Hello and welcome back. This is another video where I'll be using kinematic equations to try to solve for the motion of an object. I thought I would in this video, I would sort of start with the examples worked out in the last one with an object being thrown off a cliff. And I would just kind of change it around a little bit and we just solve the equations a little differently. In this problem, the basic scenario is down here. You have a person throwing an apple or something off a cliff, and it lands 100 meters below. In fact, let's be careful here. I suppose I said the cliff was 100 meters, so I really need to go ahead and say that there's an extra, let's just make up something. Let's say there's an extra 1.5 meters here. Up to the shoulder of the person, which may be a bit extreme, but okay, whatever. So that's the initial height. So the ball starts with a height which is 101.5 meters above the floor of the whatever valley or whatever it is. Other information you'll be given is that the initial velocity is positive 5 meters per second. I need it to be positive so that it goes up, reaches a peak height, and then falls down. Okay, so what we're trying to do is determine how long it takes to land. And we can find other things, but let's just do that. So that's our goal, how long it takes to land, to find that time. So we're trying to find time. So we need an equation that involves time and other stuff. Well, you could use either the velocity equation or the position equation, but I'm immediately against the velocity equation simply because I don't have any knowledge about the final velocity. I only know the initial velocity. However, on the position equation, kinematic equation 2, I do know the initial and final position. I know the initial velocity, and that I also know the acceleration because this is a free fall problem. Okay, we're going to assume there's no gravity that's relevant, or sorry, there's no friction that's relevant, and gravity is the only agent which acts on the ball as it falls. So if that's the case, let's kind of write my knowns here just to really highlight that. So I would say the final position, let's go ahead and say that this is x equal, actually we're not going to say x, we're going to say y. The final height is y equals 0, which means that the initial height is y equals 101.5. So I know that y final is 0 because it lands meters. Y initial is 101.5 meters. V initial is 5 meters per second. And the acceleration is equal to minus g, or minus 9.81 meters per second squared. Remember, g is the positive part of this, so don't include that extra minus sign. All right, so if I go over here to kinematic equation 2, we know about final positions, initial positions, velocity, acceleration. We've got everything we need. So our plan is to use equation number 2, the plan to find the time that it lands is to use equation number 2 to chug out time. And just a comment, this is a quadratic equation. We will need to use the quadratic formula. All right, so that is our plan. Use this kinematic equation number 2, the quadratic formula, and solve for time. just a reminder for those of you who don't remember, and I kind of muffed it there on the last video, my own little world. So we would say the quadratic formula in its kind of general form is that a times t squared, this should be whatever your variable is, but here for us it's time, plus b times t plus c equals 0. So it's, you call the coefficients a, b, and c, you add them with plus signs, that has to equal 0. And then the solution says that t equals negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. All right, so that's just a reminder of things that you know. And I expect that you do know that. So on a test, I wouldn't think quite twice about giving you a problem like this. And you would just have to know how to use a quadratic formula. All right, so now let's go through our problem. Just follow our kind of roadmap. We're going to say the second kinematic equation says that y equals y initial plus v initial t plus 1/2 the acceleration times time squared. I plug in the numbers I have here. So the final height is 0. The initial height is 101.5 meters plus the initial velocity of 5 meters per second times t plus 1/2 the acceleration, minus 9.81 meters per second squared times time squared. Okay, so that means that, well, the coefficient of time squared is a, so that means this is a, including the minus sign. This is b, and this is c. And so therefore, when I solve it, I get that the time equals negative b, I'm going to drop the units here, plus or minus the square root of b squared minus 4 times a, which would be negative 4.905, because a is half of 9.81 with a minus sign, times c, 101.5. All divided by 2 times a, but that's just negative 9.81. Okay, so we have to solve this. And so I'm going to use my calculator to do that. So just give me a second. Okay, so I've used my calculator here to crank out the numbers, typed them all in. And what I get are two solutions. My two options are t equals, and I am getting negative 4.07 seconds or 5.09 seconds. Now, both of these solve the quadratic equation, but only one of them makes physical sense. Think about the picture. It starts here and goes up and then down, so as it moves forward in time. So we're looking for an answer which is positive in time. So this is the answer I want. So you might think, well, you never keep the negative sign solution. And usually that's true, but that actually isn't necessarily right. What that problem would actually be is a hypothetical other problem you might have where perhaps instead of starting up here, what if you had started out down here at a height of 0? You know, imagine the cliff isn't there and you threw it up and then down. So given that it was here at time 0, that would mean it came from the floor at a time, a negative time value. So that would be the kind of meaning of that solution. It's when you're trying to work backwards in time. That wasn't what we had. We wanted a forward in time solution, so we went the positive number. Okay, and so that is kind of a typical kind of kinematic equation problem. You could do all sorts of other things. You could use the other kinematic equations to find the final velocity that it hits the ground with, or oh, I don't know. There are lots of variations of this. Okay, hopefully that was helpful. Give me feedback if there are things I should change. Thanks.